Welcome back, everyone. In the last video, we talked about what the derivative of a function at a point is, and one interpretation of that was the slope of the tangent line to the function at that point. For example, if we have this function here and I look at the point when x is equal to 0, and draw the tangent line through that, and ask myself what the slope of that tangent line is, well, it looks to be about -1. And that -1 is the derivative of this function at that point. Now, if I were to repeat that process for every single point on this function and put all of those derivatives together, that would get me a brand new function called the derivative function. And that's what we're going to be introducing in this video. Now, before we try and find the entire derivative function for the original function we started with, let's start by just finding the derivative of a few different points. We already know that the derivative of this function when x is equal to 0 is -1. So let's plot one point at 0, -1 to remind ourselves that the derivative at 0 is -1. And let's do that for a couple other points. Let's say I looked at the point when x is equal to 1. If I were to draw the tangent line through that point, it would look like a perfectly horizontal line. I know the slope of a horizontal line is 0, and so the derivative at that point is 0. And I'm going to plot another point at 1, 0 to remind myself that at the point where x is equal to 1, the derivative is 0. And let's do that for one more point. Let's say when x is equal to -1/2. And if I were to draw the tangent line through that point, it looks to be some positive slope, and I don't know exactly what it is. Let's say it's right around 3/4. I'm not trying to be exact here, I'm just trying to get an estimate. And so I'm going to plot a third point at -1/2, 3/4 to once again remind myself that when x is equal to -1/2, the derivative is 3/4. And if I were to repeat that process for every single point on my function, it would get me the following graph. And this blue graph here is called the derivative function because it captures the derivative of the original function at every single point. Now, coming up with that derivative function that quickly is certainly easier said than done, but there are a few things you can keep in mind to go about it in an efficient way. One thing to keep in mind that would help is that if the function is increasing, that means it's trending upwards, and if you were to draw the tangent line to any point on that interval, its slope would be positive, and so the derivative should be positive at that point. Now, on the other hand, if the function is decreasing, that means it's trending downwards, and if you were to draw a tangent line to any point on that interval, its slope would be negative, and so the derivative would be negative. Now, if you draw the tangent line and it's a perfectly horizontal line, that means its slope is 0, and so the derivative would be 0 there. And with these three things in mind, let's go back to that original function and see if we can come up with the derivative function in an efficient way. So looking back at this function, if I wanted to graph the derivative function, the first thing that I would look for is, are there any points on this function where the slope of the tangent line is 0? And for this particular function, there look to be 2 points, which happen at the peak and the valley. And if I were to draw the tangent line at either of those points, it would be perfectly horizontal. And so I know that the derivative at those points is 0. And so I know that my derivative function has to be 0 at those points. And that's where I always start with these problems to give my derivative graph a little bit of structure. The next thing I would think about is, where is this function increasing and where is it decreasing? And if I look to the left side of this function, all the way up to that first peak, this function is increasing. And if I were to draw the tangent line to any point on that interval, its slope would be positive. And so I know that the derivative function has to have a positive value at those points. Now, as I go further to the left, the tangent line is steeper, and so I know that the derivative is a larger value, and so that's why I drew the derivative function to be higher at those points. And that would give me the first piece of my derivative function. Now as I look more to the right, say in the middle of my original function, between the first peak and the valley, in that entire interval, the function is decreasing, and if I were to draw the tangent line to any point on that interval, it would have a negative slope, and so I know that the derivative function is negative at all of those points. Now, there are some points where the slope of the tangent line is steeper than other points, and so at those points, the derivative function should be a larger negative value to reflect that. And that gives me most of my derivative function. And as I look further to the right beyond that valley, everything beyond that, the function is increasing. And if I were to draw any tangent line for any point on that interval, it would always be a positive slope. And so I know that the derivative function is going to be positive on all of those values. And as I go further to the right, the slope gets steeper and steeper. And so the derivative function is going to have a larger and larger value as I go further to the right, and the derivative function that I drew reflects that. And if I put all three of those pieces together, I get a good picture for what the derivative of my function looks like. And this is a beautiful function in its own right that has its own properties, and we can study separately from the original function. Now, when you go through this process on your own by hand, it's not going to be this perfect. And that's okay. We're not asking you to be this perfect, as long as you have the main characteristics down, where the derivative is positive where it should be, it's negative where it should be, it's zero where it should be, and it roughly reflects the steepness of the original function. If you have those characteristics down, then you'll be fine. Don't worry about trying to be perfect. Now let's look at a couple of other different types of functions and try to do the same thing. Let's say I had a linear function instead. So this is the function y equals 2x plus 1. It's in that y equals mx plus b format, so we know it's a linear function. And let's try to draw the derivative function of this. And it feels a little bit weird to draw the tangent line to this function because it's linear, but just ask yourself, what is the slope of this function at any point? Well, being linear, the slope is always the same. It's always a slope of 2, and so I know that the derivative at any point on this function is always exactly 2. And so the derivative function is y equals 2, because that reflects the slope always being 2 no matter where I look. Now what if I had an even more simplified version of that problem where my function is just a constant function? Let's say the function y is equal to 4. Now again, drawing the tangent line feels a little bit weird with these linear functions, so just ask yourself, if I look anywhere on this graph, what is the slope at that point? Well, being a constant function, it's a perfectly horizontal line, and no matter where I look, the slope is always 0, and so I know that the derivative of this function is y equal to 0. And it's a perfectly horizontal line that goes through 0. And we can actually generalize those last two examples to any linear function and any constant function. So let's say I have a linear function, f of x is equal to mx plus b. And this is a linear function with slope m throughout the entire function. And so the derivative of this is just equal to m, because that's the slope anywhere I look. And as an example, the one that we just looked at was the function 2x plus 1. Its derivative is 2. Now if I have any constant function, say f of x is equal to c, its derivative is 0 because the slope throughout the entire function is always 0. For example, the one we just looked at was f of x is equal to 4, and the derivative of that is 0. Now this process of looking at specific examples and then generalizing it to many different situations is something that we're going to do often throughout this next block of the course, but these two examples are all we're getting to in this video today.